Welcome to the Deep Dive, the only place where we dig into the source material and then bring together pure knowledge and deliver it straight to your brain. Today, we are mapping the territory of a language that has arguably become the central nervous system of modern technology, Python.
And that is essential right now. We're deep diving into a language that consistently ranks in the top 3 for job demand. Our sources are pointing to average U.S. developer salaries hovering right around the $100,000 mark. But Python's appeal
isn't just financial.
Right. It's the ultimate Swiss Army knife. It starts simple, for general automation and scripting, but then it extends into the most sophisticated frontiers.
We're talking massive web applications, artificial intelligence, and even complex fields like genomics.
Which is why our mission today is to cut through all that noise. We want to deliver a clear, actionable guide to Python's most essential applications. And we're pulling nuggets from everywhere, from industry tutorials on data camp to high-level academic papers on biochemical modeling.
So let's start where Python has truly planted its flag. The world of data analytics and engineering. The fundamental question is, why did Python beat out other languages in this space?
It really comes down to the simplicity and the quality of its neighborhood,
The ecosystem.
Exactly. Python's syntax is readable. It's almost like pseudocode. That means scientists, analysts, domain experts who aren't career software engineers can pick it up fast. But the core reason is that scientific computing ecosystem, those open source
Libraries like NumPy and SciPy, they provide the performance you need without taxing the user.
And the centerpiece of that ecosystem, the tool you absolutely must know, have to be Pandas.
It's what turns raw data files into structured usable information.
Pandas is the foundation for, virtually all data manipulation. We saw a great example of the sources using a medical instruments cost data set to illustrate this. You go to CSV with a single command, and then you can just have a quick exploratory data analysis ED using functions like .head.
But the real power is in the manipulation and the feature engineering. I remember spending hours manually standardizing text fields in spreadsheets before I discovered tools like this.
It just trivializes that process. For cleaning text fields, you can normalize categories, say converting fields like sex or region to a consistent lowercase using .co.log. But more importantly, you can engineer entirely new, useful features.
Give me an example of that feature engineering.
Okay, think about raw data like body mass index or BMI.
It's a continuous number, that's fine, but often you want actionable categories. So Pandas lets you use pd.cut to turn that continuous column into buckets underweight, normal, overweight, obese,
Using defined bins like 0, 18.5, 25, 30, and p.enf. You just transform the column of numbers into a column of labels ready for immediate analysis.
That makes a complex analysis so much more intuitive. So we want to look specific patterns. How does Pandas simplify complex aggregations?
It uses .groupie. In that insurance example, if you want to know the difference in average charges between smokers and non-smokers across different regions, you don't need some complex series of nested loops or joins. You just use .groupie on region and smoker simultaneously and compute the mean charges. It's essential for large-scale analysis.
Okay, so moving from calculation.
Surgical control.
That's a perfect way to put it. Matplotlib is the absolute foundational engine. It gives you granular control over every single pixel, color, and label.
You need it for quick internal exploratory visuals or for model evaluation like plot
C4 simplify the common statistical work.
Exactly. C4 is built right on top of Matplotlib, designed for elegant, polished statistical visualizations. If you need a quick box plot of a kernel density estimate, AKE, to Z distributions, C4 cuts the lines of code you need for like 80%.
So we've analyzed the data. Now let's talk about the plumbing, the infrastructure. What does Python enable on the engineering side of the data workflow?
That's data engineering, designing, building, and maintaining scalable data infrastructure. Once you move from a notebook to production, you need workflow orchestration. You have to stop running manual scripts on a cron job.
And the industry standard for that, if you're using Python, is Apache Airflow.
Airflow is critical. It's an open source platform that lets engineers define their entire sequence of data tasks.
Cleanup, transformation, model training as directed acyclic graphs, or DAGs.
DAGs. That sounds intimidating. What does directed acyclic graph actually mean in plain English?
Think of it as a set of defined tasks with one-way arrays connecting them. Directed means that the arrows only point forward. Task A has to complete before task B can start. Acyclic is the crucial part. It means that the flow can never loop. all using simple Python code like task 1, task 2.
That reliability is mandatory for production systems. And let's talk about getting the raw material for that assembly line, because that usually means interacting with the messy, unstructured web.
Right. Data collection often involves web scraping, consuming
Structured APIs, or just making raw HTTP requests to fetch JSON data. And Python has a specialized tool for every single scenario.
Let's break down the web scraping toolkit.
Because there are 4 names every data professional really needs to recognize.
The first 2 are the fundamental duo. Requests for making elegant, human-readable HTTP requests, and beautiful 2 for taking the raw HTML and parsing it.
But that simple approach breaks down pretty quickly when you deal with large volumes of content sites.
That's when you scale up. If you're running serious concurrent scraping jobs, you move to Scrapy. It's a full-fledged asynchronous framework that handles things like managing concurrent requests, respecting delays, and building data pipelines automatically.
And then there's the final piece, the tool you need when the website is hiding its data behind complex interactions.
That's Selenium. Modern websites rely so heavily on JavaScript to render content after the page loads. If you try to scrape those sites with requests, you often just get a
Blank framework. Selenium automates a real browser, like a virtual user, so you can interact with buttons, scroll, and wait for dynamic content to appear before you capture it.
So that covers it.
Now let's look at delivery. Building APIs to structured data or models. Fast API seems to be dominating the minds of some landscapers.
It is. While Flask and Django are mature and stable, Fast API is built for speed and modern web standards. It uses Python's functions to automatically validate data, ensuring that if you expect an item as an integer, it immediately throws it forward as a string.
And it handles all the messy documentation automatically, which is a huge benefit for development teams.
Additional query parameters like search term.
Which is a great architectural example of how you move a scraping job or any Python-heavy task from a simple script to a production-ready API. It requires more than just Fast API itself, though.
Modern car body, but you need a high-performance engine to run it. That engine is Erokhane, which handles the asynchronous communication that makes the API so incredibly fast.
But even a fast engine can only run
One race at a time. How do you handle, say, 50 people requesting a script job simultaneously without the system just freezing?
That's where multiprocessing pulls in. Think of the API as a highly efficient kitchen. When a complicated order comes in, a long scraping job, instead of the head chef, the main CPU core, stopping everything to cook it, they delegate that task to another specialized chef, another CPU core. This lets the API handle simultaneous requests and utilize all the scraping jobs.
Scalability. And for persistence tracking those jobs and storing the results, you need a reliable database layer.
Yes, and that's often handled by
SchoolAlchemy. It's an object relational mapper, an ORM, which lets you interact with databases using Python objects instead of raw SQL. You define your script jobs table, connect with an engine, and then use
sessions to securely track the status and results of every request by its job.
That's a serious end-to-end data system. Okay, let's pivot now to a really beautiful field that shows Python flexibility. Computational biology and genomics.
This is where computer science really converges with the code of life. For years, genomics research suffered from the two-language problem. Researchers had to choose a user-friendly language like Python or a high-performance one like C++ or Julia for speed.
And Python is bridging that gap. You can see a simple user interface with a high-speed backend.
Exactly. When you analyze DNA or RNA, you're just treating the sequence as a string of characters. Python's simple indexing and slicing are used for basic manipulation.
But the one detail to remember, which trips everyone up, is zero indexing. A nucleotide at physical position 2 has an index of 1.
So the basic sequence manipulation
Uses standard Python functions.
Yes, operations like changing a T to a U to simulate an RNA transcript or combining sequences. It all relies on core Python string capabilities just applied to biological data.
Let's get more complex. The first material highlights of OSB. This isn't just about reading sequences, this is about modeling complex biological systems.
Right, PySV, Python systems biology. It's a revolutionary approach to biochemical models like the cascades that lead to programmed cell death or apoptosis. They're constructed as Python programs, not just lists of equations.
So the complexity is managed by the logic of the code itself.
Precisely. PySV lets researchers use specialized Python macros to define common biochemical actions like binding or catalysis. And crucially, the
the modeling process immensely.
And it also acts as a quality control layer.
Our sources noted that this programmatic approach is so robust that it can validate models against published literature and has even been used to correct subtle errors found in published mathematical models. Python is typically the work of academic biology.
And that biological application extends into modern complex areas like biogeontology.
Yes. Specialized libraries like BioLearn support standardized handling of complex omics data like DNA methylation. Like the C-index and plot hazard ratios to understand the impact of various biomarkers on life expectancy.
And finally, the cutting edge. Using AI to interpret DNA. We're talking about fine-tuning large language models for genomics.
This is crucial for understanding gene regulation.
For instance, DNA sequence classification to predict where a transcription factor might bind. Historically, LLMs required supercomputers, but this is now feasible even on
Consumer-grade hardware thanks to two breakthrough techniques.
What are those enabling technologies?
Four-bit quantization. This drastically reduces the model's memory footprint by storing its numerical weights using far fewer bits of information. Second, LoRa, or low-rank adaptation. Instead of retraining the billions of parameters in the original LLM, LoRa only adds and trains a small, highly efficient set of new matrices. It allows for parameter-efficient fine-tuning, minimizing computational costs while maintaining performance.
Python is managing everything from data ingestion on a web server to training an AI.
To predict gene binding. That covers the breadth. But for you, the learner, the critical question is, how do you actually master this language without spinning your wheels?
the consensus across
All learning materials is avoid tutorial help. Watching videos, even great ones, is just passive consumption. The only path to mastery is active coding, focusing on hands-on, real-world projects.
Endless video streams. Where can people find a good project-focused path?
MOOCs offer great structure. The course IBM Data Analysis with Python course is highly recommended. It covers the essential analytical process and even advanced concepts like overfitting and grid search. Udemy also offers massive, complete courses like 12-hour boot camps, which are often on sale.
And platforms like DataCamp and DataQuest emphasize applied skills and portfolio building.
Absolutely. DataCamp's Python Data Associate certification is designed to test the practical application of cleaning and visualization.
and DataQuest, crucially, emphasizes interactive lessons and building a portfolio from day one. This guided approach helps beginners avoid constantly having to pause and Google basic syntax.
For free and self-guided resources, we're the ultimate sandbox for experimentation.
For full free courses, free code camp on YouTube is a mandatory mention. But for data sets and hands-on low-stakes projects, the premier resource is Kaggle. You can find real-world data and see how others have solved similar problems. It's endless material for portfolio building.
Regardless of the course, we need to reiterate the management fundamentals. These are the building blocks you have to master.
They're non-negotiable. You must master clear data types, the difference between lists, dictionaries, and sets. You need fluid control over loops and conditional statements. You have to understand built-in functions like len and range. And critically, you need to know how to handle files cleanly, particularly using the with open statement.
This deep dive has really reinforced the view that Python is not just a language, it's a definitive platform for data production. The foundational knowledge pandas and NumPy is mandatory, and specialized
Libraries like PSB and BioLearn enable highly niche, cutting-edge work.
And we learned that the ability to put that analysis into production using tools like Airflow for orchestration
And fast API for deployment is what separates a proficient analyst from a professional data engineer. The best path to proficiency is still hands-on, project-based learning.
If you reflect on Python's journey from a general-purpose language to its ability to model complex biological processes like apoptosis or fine-tune an LLM to predict
For you to consider as you step into this ecosystem. Knowing that Python can handle all the heavy lifting, what groundbreaking biological or data system could you design or automate that was previously impossible?
don't just